Today I'm going to give a very broad overview of the work that me and others have been doing on trying to infer spin from the Beck's data of the photon ring. So there we go. Okay. There we go. Okay. So I'm gonna skip the big recaps of the photon ring because we've heard it a couple times in the last couple days. But right, this is a black hole. We kind of have an expectation for what they look like, and they all have this feature, a bright thin ring in their images that appears no matter where they no matter where they are, no matter where you are relative to the black hole, no matter what properties of the fluid is around them, you get this bright ring. And this ring is, of course, the photon ring. And it's called that because it's composed of photons that orbit the black hole some number of times before escaping. And because these photons are directly impacted by the black hole's gravity, the ring that they form contains information about the black hole and its effect on space-time. So it encodes information about the black hole's angular momentum and inclination relative to the observer, or the orientation of the spin axis. And so what this means is that if we look at a movie of a photon ring, oh wow, I just realized it's really laggy, huh? Is it laggy for you guys too, or is it just me?
It's fine. It's fine.
Okay, sweet. So what this means though is, if you can observe the photon ring, you can infer potentially the properties of the black hole spacetime based on how the morphology of the photon ring appears to you. So we've been studying this, and a big question we've been trying to answer is how do we go from an image or data on the ring to measurements of these quantities? So to try and solve this problem, we made a super dense grid of photon ring images using CurbAM, which is this amazing semi-analytic ray tracing engine developed by Daniel Palumbo. It lets us produce images of the photon ring, millions of them on a very short time scale, with all sorts of parameter combinations ranging from the space-time parameters like spin and inclination, but also a whole bunch of other parameters related to the fluid flow around the black hole to see how the photon ring evolves. And then we put them through these images through a variety of neural networks in order to attempt to measure spin and inclination from the images. And so we took this big data set and we trained a convolutional neural network, which is a special type of machine learning algorithm that can look at features in an image and then use that to make inferences and sort of teach itself what makes different images different. And this was the results that we presented. Basically, we found that on nice, clean images of just the n=1 photon ring, even at Beck's resolution, it is sufficient to recover angular momentum from the images. So what you're seeing here is you're seeing the actual spin of the image that you input and then what the network predicted. And even when the image is convolved with the Beck's resolution, or the expected Beck's resolution up to 6 to 10 microarc seconds, you're able to get very consistent recovery up to around 10%, which is really exciting because it suggests that Beck's will see the n=1 photon ring. We're hoping, and that seems to be the features of it seem to be sufficient to constrain spin and inclination, which is a really good check. But the thing with convolutional neural networks is that they don't tell you how they did it, and so a large part of the work we did on the paper involved examining how the neural network figured out what spin corresponded to what image and what features it was looking at. And through our investigation, we found that it really liked this quantity denoted W_B here, or B var phi. It really liked this quantity corresponding to the brightness asymmetry as a function of angle. And so what this quantity is it's just you take the photon ring that you see and you measure how bright the intensity is along the ring as a function of angle. And then you measure that distribution ends up being kind of Gaussian-like, and then you measure the width. And what we found was that this width correlates really highly with the spin, with the inclination of the black hole, and it doesn't vary too much with the spin. And so what you're seeing here in white and on this graph is a GRMHD, this quantity measured on a GRMHD, and you can see the curve that results. And then this orange curve is a CurbAM curve, a CurbAM simulation, so semi-analytic simulation at the same inclination. And what you can see is if we compare it to a different semi-analytic simulation at a very different inclination, it's very distinguishable. And we made these plots showing what this looked like across the sort of Kerr parameter space. And it's remarkable how predictive it is for inclination. And so if we want to infer spin, there's a lot of degeneracy between between the way spin makes a black hole look and the way inclination does. And so being able to constrain the inclination sort of freely of spin is a really powerful tool to make spin constraints down the road. And so we took what we learned from these semi-analytic simulations and we applied them to GRMHD simulations made by Charles Gammy and his students. And what we found was that even though we were training on only semi-analytic simulations, which are much, much simpler than the full GRMHD simulations, we were still able to get meaningful recovery at a variety of spins and inclinations. And even though it's not perfect, it's a very promising start for how we can go from even just a couple of these observables to a constraint on spin and inclination. And so this was a really exciting outcome. Of course, all the stuff that I showed you before of the training we did, where we trained on, this neural network and we tried to extract images we tried to extract spin and inclination. This was all done in the machine learning set. And this was all done on just images of the n equals 1 photon ring. But that's not what Bex is going to see. Bex is going to see images of all the photon rings and the direct emission sort of added together, which is really complicated and a much harder problem to solve. So I've been working with a student at UCSB. Her name is Courtney Dong, and she has been working on developing a convolutional neural network that extends what we did to measure spin. But instead of measuring spin, what this network does is it takes in an image and it spits out another image. And the image that it takes in is an image that has multiple subrings, as you can see here. So this image on the left here has both a thick sort of n equals 0 mimicking ring and a thin n equals 1 mimicking ring. And this is the real n equals 1 mimicking ring. And then it cleans the image of the diffuse emission and leaves just the n equals 1, the perceived n equals 1 subring. So here's it operating on a couple more items, a couple more examples. You can see this doesn't look like any black hole simulation you've seen because we use the M ring to go beyond the Kerr parameter space and build robustness, but it's basically able to recover the n equals 1 subring from an image contaminated with other emission really well, which is exciting because if you take this network and then apply it to a real Kerr-BAM image like this, so this is of a real n equals 1 subring plus n equals 0 emission, it cleans out the n equals 0 emission and you're left with just the n equals 1 subring very effectively. And without any additional training, it works out of the box pretty decently on full GRMHD, which is really cool. This is not like perfect, but given that we're only training on pure clean M rings, it's really nice. So this is she's preparing a paper for submission on this result right now. I also have another student that has worked on the tool methods end of this. So Franklin Meyer has been working on tools to very quickly extract properties of the black hole photon ring from images on very rapid timescales. So extending a method we published earlier this year, Frank has written a software package that we're going to publish soon that does feature extraction like this, hundreds to thousands of times faster than existing tools. And this is really useful for analyzing these large databases. We applied it to Courtney's neural network. And so what we had, for example, an n equals 0 diffuse image here and an n equals 1 ring here. And we used his software to extract the radius and brightness as a function of angle. And what you can see here in blue is this is what we expect. The blue is what we want to get. And then the white is what we actually got, which is really, really exciting. They match. And more importantly, not only do they match, they're distinct from the full image, which is shown in yellow. So this is a really nice sanity check that we're actually, when we clean the image using Courtney's neural network, you're actually getting properties that correspond to the thin subring and not the thick one. And you can imagine how powerful this is going to be when we apply it to Beck's images. So I'm almost done now. So what's coming up next? So we've got these nice neural networks and we want to refine them, refine these existing proof of concept networks and make them better, basically. Like I showed the GRMHD, that was nice, but as a proof of concept, but it definitely can be improved and we're going to improve that. All of our stuff so far has just been on time averaged images. And so we'd like to address the problem of variability. I believe it can be trained out. I think we can address this problem via a sufficiently large training data set and get some meaningful estimates, even though they won't count as detections or I still think we can do something useful on training on time variable sources. And this is something I'm working on with Alejandro. And then finally, we we all the stuff that we did, all the machine learning stuff that we've shown so far is on very basic neural networks. There's a lot more advanced tools that we can take advantage of, especially with recent advancements in transformer architecture and attention, which I think will be very useful for a noise dominated problem like Beck's. And so there's a lot of really exciting stuff happening, I think, along this line. And my hope is that we'll have a bunch of advanced tools that will make meaningful spin and inclination extractions on Beck's data when the time comes. So thank you for listening, and thank you to my collaborators as well for the opportunity to give this talk and all this great work that we've been doing together. I'm happy to take any questions.
Great. Are there questions for Joseph? I have one, maybe just to get things started, which
Sure.
is early in the talk, you said that, you said working backwards from the convolutional neural network, we can figure out what it was paying attention to, what it was focused on, and you used the right. So how do you identify that feature as being the one that it's focused on?
So I'm really glad you asked that. I wanted to keep it kind of top level just for the talk, but I'm happy to expand on any of these technical details. So the way we did this, the convolutional neural networks are great. They use the full information in the image, but you have no idea what exactly they're doing. So in parallel to the convolutional neural network, we developed a separate machine learning algorithm. We use something called a gradient boosted regression tree. And we feature extracted using Frank's tools every possible image feature we could think of. And then we selectively removed them until the performance sort of plateaued. And this told us what features of the images were giving comparable performance to what the convolutional neural network could achieve. So the CNN set the absolute upper limit of what was possible from the images, and then we approached it using a smaller and smaller subset of observables. And eventually we got down to really just the maximum diameter and the brightness along the ring.
So it's a kind of dropout test.
Exactly. And I think this will be really effective for taking these tools that otherwise are black boxes and making meaningful progress with them.
Thank you, Daniel.
Great. Thank you, Joseph, for a lovely talk. So the situation where the n=1 ring acquires I believe you said a wider brightness profile, which I guess in some sense is a flatter brightness profile in azimuth as a function of spin. So I know you and I chatted, I think even as far back as Beck's Japan, about how I was puzzled by this. So if memory serves, your training set only includes models that have a purely equatorial magnetic field. Is that right?
Yes, that's correct. And the training set that we did for the machine learning is only operating on a really small subset of fluid parameters. For the paper where we moved to GRMHD, this is operating on varying a lot more parameters, and that's why the performance is so much worse than it is in the original paper.
I see. Sorry, you trained on a wider set of Kerbam models before applying to GRMHD, or did you train on GRMHD? I see, okay.
We trained on a wider set of Kerbam models.
Because I guess, ignoring for now all of the spin measurement, which is awesome, I would love to just see a summary of that behavior of the n=1 brightness profile widening as a function of, the Kerbam parameter space or just across GRMHD. It seems like you're able to measure this in GRMHD. Because to me, it seems like I can construct scenarios where it should certainly happen for a purely equatorial emission geometry and purely toroidal fields. But then it feels like I should be able to play games with the magnetic field to make it go away or have different patterns. And so I at some point, I would love a summary figure of just what the heck that signature is doing in GRMHD. I'm sure I'm not trying to put you on the spot. I don't know if you have it now, but
no, I don't have it in this.
Very interesting.
I don't have it in the slides, but in the paper, each of these figures showing the variation in the Kerbam models is coupled to a spread showing how much varying the fluid parameters varied the quantity that we measure here, and it is quite high. So you're absolutely right. Even within Kerbam, we can play games and get it to vary quite a bit. And indeed, you see that even though this seems like a really straightforward, like you measure this quantity and it just tells you the inclination, when you look at it, when you apply it to the GRMHD, you can be off by as much as 20 or 30 degrees. And like that's absolutely because the geometry is so much. You can get really complicated with this. The nice thing about this is that there is an analytic motivation that we found for it, just based on the Doppler boosting. That's sort of disconnected from spin to an extent, but it is absolute. This is really just showing what you can do with a couple parameters, and down the road we're gonna have to account for more and more of these degrees of freedom in the physics, and that's how. And like it's gonna need more than this for sure. So, and I can send you that figure after the after.
No, no, I understand. I mean, I also think, spin is going to show up in all kinds of subtle ways that we don't think about in model images, and all of these semi-analytic tools, including the ones that are now vastly more advanced than old dingy Kerbam, they all feel these signatures, and it's all in there. It's not a black box. It's just yeah. So anyway, there's lots of hope for these things showing up. Thank you, Joseph.
Sure. You say old dingy Kerbam, but the advancement of Kerbam like changed the landscape for how we were able to do this. So I just don't just throwing that out there.
So that's very sweet of you, Joseph.